Okay, 7:20. Let's get started. Okay. Very good evening, everyone. It is a great pleasure to speak in front of our young, bright audience. My name is Xiaobo Qu. I'm a professor with School of Vehicle and Mobility at Tsinghua University at Beijing, China. I used to teach in Australia for 6 years from 2012 to 2018. And I taught in Sweden, Europe, for 4 years, from 2018 to 2021, before returning to my home country in December 2021. My research area is focused on next generation transportation system. Today, I'm very delighted to present with you the future transportation systems, highlighting a few trends and driving forces using a few key studies that my group has been doing in the past 5-6 years. This is a very exciting area, and we need a young, bright brain to join us for further development in this area, in transport and vehicle. This is my email address. If you are very interested in my topic, send me an email and we can communicate. Okay, I will start with the economic map of two major countries on Earth, whose leaders just met with each other yesterday in Bali, Indonesia, after not seeing each other for a very long period. As can be seen in the two diagrams, see the two diagrams, 1.8% land in the United States contribute half of their GDP, and 0.23% of land in China contribute half of all GDP. Another country with massive land, Australia, 7.7 million square kilometers, is 45% people and 65% economy in two cities, in Sydney and Melbourne, two major cities in that country. The reason I mention this, I use this diagram to demonstrate, to emphasize that urbanization, you see the first sentence, urbanization is unstoppable, is an unstoppable trend. And there are huge economic, cultural, political, educational, and health benefits. However, urbanization comes with cost. The most important, the most difficult one is traffic congestion, which substantially affects the livability of a city, and the well-being of the residents living in the city. So we don't like traffic congestion. And even worse, the rapid urbanization amplifies the most fundamental problem of transport, which is the asymmetry between transportation demand and transportation supply. I will use these two diagrams, two videos to explain. The left-hand side is transportation demand. The right-hand side is transportation supply for Beijing subway system. Left-hand side, for transportation demand, we always have very heavy traffic on the morning peak hours, right? On the morning peak hour from 7 o'clock to 9:30, very, very crowded, very, very heavy traffic. While the volume at night is very low. The volume at night is very low. The demand is changing. That means the demand is changing dynamically. From time to time, the transportation demand is different. On the morning peak, it's very crowded. On the night, low demand period, only a few users are using our transport infrastructure. In contrast, the supply in the right hand is relatively stable. Why? Because the supply is determined by what? By infrastructure, right? By the transport infrastructure. If you have transportation infrastructure, you have the capacity for transportation infrastructure. The capacity is a fixed value. It is not wise for us, for the designers, to use the highest demand, that means the morning peak, to design our infrastructure, as it will be a huge waste. We usually use 75 percentile. 75 percentile, that means under 25% of the time, we are congested. 75% of the time, no problem. However, with the rapid urbanization, we experience congestions at many more occasions. For example, in Beijing, the congestion period, we are living in Beijing, the congestion period is not limited, certainly not limited to the 25% of the time. These are two examples. These are two examples during the peak hour. You see left-hand side, the peak hour in Tokyo, Japan. It's very crowded. You see the train staffers have to push the passengers into the train. While during the off-peak hour, here, even in Mumbai, India, the train is almost empty, right? So the peak hour, very crowded. The off-peak hour, no traffic, no users. And, in the past several years in Beijing, during the peak hour, in some famous train station, is not the train is full of people, full of users. It's the whole train station occupied by users, by the residents, commuters. So after explaining this background, in the following slides, I will introduce a few case studies, and I will use this case study to demonstrate what will happen in future. These few case studies that were done by my group in the past several years, and I want to share with you the latest progress in the area of transportation and the vehicle. Okay, when we consider the traffic congestion problem, we will need to deal with the traffic bottlenecks, right? So for any problem, any issues, we first to find the bottleneck, to find the critical point. And what are the most common traffic bottlenecks? Intersections, right? Intersections. And we only have partial time, a certain percentage, less than 40%, even less than 35% for one direction. The time is the green time that can be used to discharge the traffic. So take a look at this video. I will introduce what we can do to solve the problems in the video with connected automated vehicles in our first case study. So I will introduce, 3 large case studies in today's lecture. Okay, take a look at the video first. Okay.
Then the next, and then you. Only intersection. You always watch unfold the fun.
Can you hear the voice? You can, right?
Yes.
Okay.
Fundamental problem of traffic. On green, the first car accelerates, and then the next, and then the next, and
okay.
Then the next, and then you, only to catch the red. Had the cars accelerated simultaneously, you would have made it through. Coordination, not cars, is the problem, because we are monkey drivers with slow reaction times and short attention spans. Even if we tried, getting everyone to press the pedal on 3, 2, 1 now would be challenging. This discoordination limits how many cars can get through an intersection, and when one backs up to the next, that's when city-sized gridlock cascades happen, taking taking forever to clear. In general, more intersections equals more discoordination, which equals more traffic. This is the motive behind big highways. No intersections. Splits and merges, yes. Intersections, no. No stopping, no coordination problems, no traffic. Well, that's the theory anyway. Intersections outside of a highway will back up onto it, again, because human reaction times limit how many cars can escape the off-ramp when the light changes. But even without intersections, there would still be traffic on the highway. Traffic can just appear. Take a one-lane highway with happy cars flowing until a chicken crosses the road. The driver who sees it brakes a little, the driver behind him doesn't notice immediately and brakes a little harder than necessary. The driver behind him does the same until someone comes to a complete stop. And oh look, cars approaching at highway speeds must now stop as well. Though the chicken is long gone, it left a phantom intersection on the highway. This is what's happened when you're stuck in traffic for hours thinking there must be a deadly pile up ahead, and then suddenly the traffic's over with no wreckage in sight. To your relief if you're a good person and mild annoyance if you aren't. You just passed through a phantom intersection, the cause of which is long gone. And this phantom intersection moves. It's really a traffic snake slithering down the road, eating oncoming cars at one end and pooping them out the other. On a ring road, a single car slowing down will start an ouroboros of traffic that will last forever, even though there's no problem with the road. If the drivers could coordinate to accelerate and separate simultaneously, easy driving would return. But they can't, so traffic eternal. On highways, traffic snakes grow if cars are eated faster than excreted, and they shrink if excreted faster than eated, dying when the last car accelerates away before the next car must stop. Now, in multi-lane highways, there needs be no chicken to start gridlock. A driver crossing lanes quickly with cars too close behind is enough to birth a traffic snake that lives for hours and leagues. It's this quick crossing that causes drivers behind to overbrake and begin a chain reaction. But we can make traffic snakes less likely by changing the way we drive. Your goal as a driver is to stay the same distance from the car ahead as from the car behind at all times. Tailgating is trouble, not just because it makes accidents more likely, but because you as the tailgater can start a traffic snake if the driver ahead brakes. Always in the middle. This gives you the most time to prevent overbraking, but also gives the driver behind you the most time as well. And when stuck in traffic, this rule would get all cars to pull apart the snake faster. That's the simple solution to traffic, getting humans to change their behavior, perhaps by sharing this video to show how and why traffic happens, why tailgaters are trouble, and how we can work together to make the roads better for all. The end. Except, yeah, wishing upon a star that people are better than they are is a terrible solution every time. Instead, what works...
Okay. In the following, I will introduce that what we can do to resolve the problem with self-driving vehicles. Okay? Okay. So for human drivers, as mentioned just now, we have limitations. We have reaction time, we have slow reaction time, we are not cooperating with each other, we made mistakes, right? It seems that not, impossible or not very likely to solve this problem if we are the driver. We as human drivers, at the very origin of the problem is our own limitation, right? It's very unlikely that people's reaction time can be shortened, right? It's not likely. It's unlikely that our perception range, the perception range can be enlarged. However, with the emerging in ICT, information and computing technology and vehicle technology, we are in the process of fundamentally resolving this problem through connected automated vehicles, which will be our first case study, as I mentioned just now. We propose modernized transit that will be our second, later I will introduce, second case study. And we propose the low altitude vertical transportation, which I will introduce in the case study 3. Okay, the first case study is to use connected automated vehicles or connected self-driving vehicles to dampen the oscillations or to solve the problem just now, the snake problem just mentioned in that video. And we want to get rid of the stop and go activities, or academically, the oscillation, stop and go activities. As I mentioned earlier, with human beings, with human drivers, we have our own limit. We have reaction time. The drivers are different from one another. And your reaction time is different from your neighbor's reaction time. And we are unwilling to cooperate, or even if we have willingness to cooperate, we don't know how exactly we can cooperate to maximize the throughput. These are the reasons that above mentioned problems. In order to resolve the problem, we as vehicle engineers, we developed the connected vehicles and automated vehicles, mainly, as I mentioned just now, attributed to the recent development and progress of information and computing technology, the vehicle technology, and very recently the AI technologies. The connected automated vehicles don't have reaction time, right? They don't have reaction time. They are robots, and they have much larger perception range than human drivers, who can only rely on our own eyes, right? The connected automated vehicles, they have the driving range much larger than the human drivers. However, for a single connected automated vehicle, the enhancement, the improvement in efficiency is rather limited. What if we have many more vehicles which are connected, automated, and cooperative? What will happen? Okay, let's take a look at these two videos. The upper video, you see the upper video, the x-axis is the time, you see the red signal, green signal, red signal, green signal, red signal, green signal, red signal, right? The time. And the y-axis is the location, is the position of the vehicle, right? So for each line represents the trajectory of a vehicle, the time, position, trajectory of each vehicle, right? Okay, let's take a look at the video again. As a normal driver, in the traditional intersection, which is the upper video, we will follow the speed limit, right? You are a normal driver, you will follow the speed limit. The speed is the slope of the trajectory, right? You follow the speed limit to approach the intersection. When you see the red signal, and you will decelerate, right? You will decelerate and stop in front of the stopping line. And wait for the green signal to discharge. When we see the green signal, what will happen? What will you do? You will have 2 seconds of reaction time and accelerate from speed of 0 to speed limit to pass through the intersection, right? That's the whole process. You decelerate, stop, wait, you see the green signal, you have reaction time. After the reaction time, you accelerate from 0, and then you want to discharge the intersection. So here you take a look at the upper video. You have 3 problems, right? The bottleneck is in the intersection. However, in the intersection, you have the lowest efficiency. You have the worst efficiency because you have the reaction time here, 2 seconds, green time wasted. You have stop and go activities in the bottleneck. Stop and go activities, that means you have higher energy consumption, you have lower speed, you have more probability of making mistake, and you have safety concerns if you have stop and go activities, because people are different from one another. And also here, the speed, average speed is very low, right? Very low speed. If you have very low speed, that means when you discharge the intersection, you take longer time to discharge the intersection. So no good. The system is no good. What should we do? You see the lower video. You focus on the lower video. What with the connected automated vehicles, what we can do is to decelerate in advance. You see this vehicle, decelerate in advance, and then you accelerate. By the time when you arrive at the intersection, you see the onset at the very beginning of the green signal. You use the speed limit, the highest speed, to discharge, to pass through the intersection. Then you see the capacity here is much higher. The capacity here is much higher. So you use the highest speed to discharge the intersection. And there is no reaction time here. There is no reaction time. And people are following each other to discharge, to pass through the intersection. That means you have no stop and go activities. You have less probability of making mistakes. If you check the overall performance, you have the travel time, you have the reduction of travel time, you have the reduction of energy consumption because you avoid the stop and go activities. You have the higher throughput, you have a higher capacity for each and every second of your green time. Your green time is better utilized. And in terms of safety, it's much better as well, because here you have stop and go activities. You might have mistakes. If you have mistake, you have big mistake, you have collision. But here, you don't have stop and go activities. People are easier. It is easier for people, for drivers to follow each other to pass through the intersection than stop and go activities. So you have travel time benefit, you have energy consumption benefit, you have safety benefit. For this kind of, if all you have the connected automated vehicles. This is another comparison when we consider two directions, the two traffic flows. Comparing with no control scenario, especially for the queue length and delay, much better for all connected automated vehicles. Much better with the correct control approach. Okay, then you may ask, now we only have a very small fraction of vehicles that are connected automated, right? You don't have 100%, and the previous example, you don't have 100% connected automated vehicles. What we can do? If you take a look at the sub-figure B, only 10% are connected automated vehicles. That means out of 30 vehicles, you only have 3 are connected automated vehicles. Under this case, we will not be able to control each and every vehicles, right? we can still regulate these 3 vehicles, right? We can still regulate the trajectories of these 3 vehicles and influence other vehicles to have a collective benefit. Okay. And we can regulate the vehicles for these 3 connected automated vehicles, and then we regulate other vehicles. So we influence other vehicles. So this example shows the platoon of 30 vehicles. A platoon of 30 vehicles, that means the vehicles are successively arriving one by one with a very similar time difference from one vehicle to another vehicle. In other words, the arriving pattern is uniform arrival. In the left-hand side, all the vehicles are traditional vehicles. That means 0% connected automated vehicles, and you have the stop and go activities. You have the oscillation, right? While the right-hand side, with 10%, with 3 vehicles are connected vehicles. These 3 vehicles become the leading vehicles of the 3 different platoons. You see, the leading vehicles followed by 7 traditional vehicles, the human manual vehicles, human-driven vehicles, and the second green time, you have the leading vehicle, the platoon of 7 human-driven vehicles. And the third one is also okay. So that means you have 3 platoons, and you have three platoons, and we can minimize the stops and enhance the safety, efficiency, and energy savings. So you see, for this scenario, you only have 3 stops, right? The first 3 vehicles, they will have to stop. For all the other vehicles, they only have fast, slow, and fast. They don't have stop and go activities, right? And can be seen in this diagram, the sub figure, C, D, and S, referring to the travel time, the energy consumption, and safety. We can make our transport system safer, faster, and greener for each and every vehicle. Almost collective effect is very substantial, especially for safety. You see the safety. The difference gap is very substantial. Okay. When it comes to the multi-lane, multi-flow system, you have left-hand vehicle, you have through vehicle, you have right-hand vehicle. So when it comes to the multi-lane, multi-flow problem, the bottleneck is always the left-handing problem. So in the right driving system, such as in China, in the left-handing system in Australia, in UK, in Singapore, the problem is the right-hand problem, right? Is the big 10, is the big 10 problem. For the through vehicles, you see, take a look at this diagram. This diagram, the first one. For the through vehicles, you have 3 traffic lanes, right? You have 3 through lanes. If you have green signal, all the vehicles in these 3 through lanes can discharge, right? Simultaneously. They can discharge together. So the efficiency is high. But you see the left-handing problem. The left-handing vehicles, you only have 1 left-handing lane. And the opposite direction, you also have 1 left-handing lane. 1 left-handing lane, 1 left-handing lane. If you give the signal to those left-handing vehicles, the green signal, these 2 lanes, this 1 lane and this 1 lane, this is the opposite direction left-handing vehicles. These 2 lanes blocks the whole traffic because all the other vehicles, they are not allowed to discharge because otherwise there will be conflict, right? So that means this green time, the utilization is very, very low because you only have 1 lane. The vehicles in 1 lane can discharge in this green time for left-hand vehicles. So this is the problem we want to resolve. This is the problem we want to resolve. So now, if we have connected automated vehicles, we can reorganize the traffic flow in real time to separate the left-handing vehicles and the through vehicles. So take a look at here. You're given any combinations. The black cars are left-handing vehicles. The white cars are the through vehicles. Through a vehicle sorting method approach, we can reorganize the traffic flow. We put the 3 left-handing vehicles ahead of the 3 through vehicles. Then we give the left-handing signal, and all 3 lanes can be used for the left-handing vehicle purpose, right? So the efficiency can be tripled, increased 2 times. And then we give the green signal to the through vehicles. All 3 lanes can be used to discharge. Take a look at this video. So we have any combination, and for this combination, we are using 4 steps. That means less than 6.5 seconds. So we reorganize the traffic flow. All the left-handing vehicles are ahead of the through vehicles. The left turning vehicles, you give the left turn signal, and all three lanes can be used for left turn purpose. And then we give the through green signal for through vehicles. All the three lanes can be used for the for the through vehicles. Okay. Just now I was not allowed to unmute myself, so now you can see my voice, right? Okay. Now we finish the multi-lane system. So another problem is about freeway. You may notice that when you are driving on the freeway or you are riding on the freeway, you may notice that there are actually for this example, there are actually 3 traffic lanes in this example, but only 2 of which can be used for mobility purpose, right? The other one is only reserved for emergency vehicles, right? Emergency vehicles. However, over 95% of the time, nobody is using the emergency lane. So in the past, with the traditional vehicles, there is little we can do. We have to ensure that the absolute priority for emergency vehicles. That means for ambulance, for police car, and for fire engine. Right? Okay, in the past, with the traditional vehicles, there's nothing we can do. We construct 3 lanes, but we can only use 2 lanes, right? It's a waste of infrastructure capacity. Nowadays, with the connected automated vehicles, we can reorganize the traffic flow. As I mentioned just now, if there is no emergency vehicle in the system, all the lanes, we use all the 3 lanes. All the lanes can be used. If there is any emergency vehicle coming over, we can reorganize the traffic flow to clear the 50 meters in front of the emergency vehicle. Guarantee the absolute priority for the emergency vehicles, guarantee the speed of the emergency vehicle. We will have a much better system with not only good for the social vehicles, because for social vehicles you only have 2 lanes, but now you have 3 lanes can be used. But also for emergency vehicles, because for emergency vehicles, we guarantee there will be no any vehicles in the 50 meters ahead of the emergency vehicle. Guarantee is absolute priority and is speed. These are some simulation results, and that were done by my group. If any fire engine coming over or ambulance, police car, and they will be given the priority and make sure the speed will not be affected and arrive at the incident site as soon as possible. Ambulance arrive at the incident site as soon as possible. Okay, that's the end of the first case study. That's the case study 1 for the connected automated vehicles. And now let's shift our topic to the second case study, a new transportation mode, a new public transport mode, and modularized transit. For most commuters in a large city, the public transport is always the first option. It is cheap, it is green, it is sustainable, right? However, we have a lot of complaints, right? We are not happy with public transport. We have a lot of complaints. First of all, you see the complaint number 1. It stops at each and every station. It stops at each and every station. Even if only one passenger alights or boards, the whole bus had to stop. The rest users will have to waste their travel time. So for a normal bus with 50 people, so if only one passenger wishes to get off, the rest 49 passengers, the travel time of the rest 49 passengers will increase because they have stopped and accelerate. They have this activity, which is no good, right? So the first problem, we don't want to have stop at each and every station. The second problem is inconvenient transfer. Because roughly in Beijing, for the other trips, over 35% trips will need transfer to complete, to finalize their trip, their origin to destination. For each transfer, you have to stop, and you might need to change platform. So for some station, you have numerous platforms, and you need to wait, right? You need to wait for the connecting bus. So on one hand, others, and we mentioned just now, waste their travel time. On the other hand, your own travel time, the uncertainty will be increased significantly, right? You also have to risk. You also have the risk of missing your connecting bus, and you don't know the route from one platform to another platform. You take a longer time than necessary, and then you miss your connecting bus. It's very likely. So this is the second problem, inconvenient transfer. The third problem is the wasted capacity. You always have crowded. You are always crowded during the peak hour. But however, during the night time, even if only one passenger on the whole route, the whole huge bus has to operate. It is very wasteful when it comes to energy consumption, the operating cost. For the whole trip, for the whole route, you only have one passenger, but you need to the bus, the big bus, need to operate. So that is very wasteful. So how to deal with this problem? Using the traditional buses, it is unlikely to resolve the problem. But with the connected automated vehicle technology, it is likely that two cabins can be connected to couple or decouple via emotion. So one of our collaborating partner designs a modular bus, taking advantage of the recent progress of information computing, control, connected automated vehicle technology. The vehicle, they call it pod or cabin. The cabin can couple or decouple while in motion, while all those cabins are moving. So the passengers can move from one cabin or one pod to another cabin while in motion. So then this system can resolve the three problems that I mentioned just now. During the morning peak hour, we can have multiple cabins linking together, maximize the utilization of transportation infrastructure, maximize the efficiency. While if somebody, the first problem, take a look at back, the first problem is stop at each and every station, right? If you have 6 cabins linking together, during the morning peak, if one passenger wants to alight, we can, for all the alighting passengers, they transfer to the last cabin, and then we get rid of the last cabin for alighting and boarding purpose. And for all the other passengers, we don't need to stop. We don't need to waste the travel time, right? So we solve the problem 1. The problem 2 is the inconvenient transfer. As I mentioned just now, as can be seen in the video, the passengers can be transferred from one cabin to another cabin, right? While in motion. And then, so for the transferring cabin, you can get rid of the transferring cabin, and the transferring cabin can link together with the vehicles in another direction, just like this vehicle. They can go to another route, linking together with other vehicles. So then solve the second problem of inconvenient transfer. The third problem is during the off-peak hour, during the nighttime, is very wasteful in terms of the energy, in terms of the energy consumption, in terms of the operating cost. So for this problem, if you during the morning you have 6, 7 vehicles linking together, but during the night you only have one vehicle, in service, all the other vehicles go back to the depot for charging, right? For charging. So if the demand is low, the most vehicles can go back to the depot for charging. So they don't need to operate. So in sum, what we can do is that during the peak hour, the multiple vehicles can be connected and reduce the congestion because the road utilization rate is higher. So for vehicles, between one vehicle and the subsequent vehicle, you have 2 second time difference. That means this 2 seconds, if the speed is 16 meters per second, that means the distance between the first vehicle and the subsequent vehicle is 30 plus meters. But with this system, all the vehicles are linking together, the infrastructure utilization rate, the density is much higher, right? During the off-peak hour, a small number of vehicles can satisfy the demand. So improving the energy efficiency as well as the service quality, because during the off-peak hour, it can operate like taxis, right? So my group has done a series of products in the vehicle level because we have we have this kind of next generation buses and also the connecting parts. We also have done a lot of work in the operational level, in the design level, in the planning level. We have already have the vehicles, and we are now keeping to improve it. So we aim to replace many taxis because for taxi you only have one driver and one passenger, right? It's not, the efficiency is not high. The car occupancy is not high. And we wish to occupy a great portion of the market share. So in our team, we are also using the discrete choice model to estimate the market share of this new mode, competing with the buses, traditional buses, competing with the taxis. The new market share for buses, for cars, for this new mode will be different than they are today. This is a very interesting extension. This is a very interesting extension. As all vehicles are connected, or physically connected. They are physically connected. We can certainly realize the intercharging, right? Intercharging from one cabin to another cabin, intercharging from one vehicle to another vehicle. In this regard, we can have a small local energy cloud system. Namely, if you need some energy, if you are lack of energy, and you can buy or borrow some energies from your neighboring vehicles. So you link with your neighboring vehicles, intercharging, and then you get energy from your neighboring vehicles. With this, we will no longer to have the range anxiety, right? We will no longer to have a range anxiety. We also don't need to have huge battery. Consider your own driving behavior. Your remaining battery are always greater than the kilometers you want to travel for a given day, or at least is a very, very high probability your remaining battery is greater than your kilometers you want to travel. That means you have the reserved energy for sale, right? For for lease, for sale, to borrow the energy to your neighboring vehicles. Considering the scenario that, another scenario, or wireless charging technology have made breakthroughs. So we can have wireless charging with 70% efficiency while all vehicles are in motion vehicles, and another vehicle, they have the distance gap of 20 meters or 25 meters, you have 70% efficiency. Then we will have an energy cloud system for the whole city, right? Instead of a local energy cloud system, you will have energy cloud system for the whole city. Under this case, the energies can be transmitted from one vehicle to another vehicle via wireless charging. And then the energy can be allocated based on the demand, based on the need, right? So now the question is, in Europe, I attended quite a few meetings in this area. They wish to establish 65 million charging points before 2030. They want to establish 25 million charging points before 2030. And consider the establishment as the precondition. Consider the establishment of this 65 million charging points as the precondition for transportation electrification. If we have this kind of intercharging system, we are either modularization, physically connected and commit the energy transmission, or wireless charging, not physically connected, but wireless charging has made breakthrough. The energy can be transmitted through wireless charging from one vehicle to another vehicle. Will the establishment of the charging point still be precondition for the transportation electrification? So on this topic, you see the diagram. You see this diagram. On this topic, we have established a model. We have two findings. Today I'm not going to introduce the technical details. Today I just introduce some findings, some performance, some benefit that using connected automated vehicles and using new emerging transport mode, using emerging technologies. The two findings: number one, we don't need to have so many charging points, right? You see, we don't need to have so many charging points. We only need to have less than 1/3 of charging points. Number two, our battery size can be significantly smaller than it is today. So we don't need to have huge battery, because if we have the range problem, we can always borrow energy from our neighboring vehicles. We have to consider, the technological development of charging devices, either wireless charging or physically charging. We need to consider the charging technologies with the charging infrastructure planning. Because if on 2030 you have 65 million charging points, but you made the breakthrough, you have the wireless charging from one vehicle to another vehicle. So what will happen? You need to get rid of these charging points, right? You need to remove all those charging points. That's a waste of the construction, maintenance, all the costs, and the removal cost. Okay, that is the end of the second case study. We are not going to have any class break, and I will finish the presentation, and hopefully we will have around 10 to 15 minutes for the questions and answers. The case study 3 is the low altitude vertical transportation system. So this is the vision that proposed by my group for the low altitude vertical transportation system. This figure was drawn by my group. This is in Beijing. You see the CCTV. You have the drones for the logistics, for the parcels. You have the flying vehicles. You have the modular buses, modular cars. You have high-speed rail, right? The drones, as you can imagine, drones can be used for logistics purpose, right? For the parcel, for delivering parcel from one area to another area. Certainly, we need to examine, the problems like noise, right? You have the privacy issue, and you have the regulation issue, right? But we are certain that these issues can be resolved. Let's consider the current parcel deliveries in your own country. The parcel deliveries, it's more or less like this kind of system. A truck loads parcels from all the customers at a warehouse or depot. Visits a sequence of distribution points. So you see, this is the circle. You visit a number of distribution points or distribution centers, and return the warehouse. So you see that this is the truck, and then for this distribution point, you will have at each distribution point, you will have a lot of pillars. Usually in Beijing is tricycles or three-wheeled vehicles, tricycles that can easily access the residential area. They are responsible for the last segment delivery. For each pillar, will travel from the distribution point, deliver the parcels to the end users, and return to the distribution center. This is how most of our current carrier service work. How we expect they to work. In the United States, they are also examining the possibilities of using drones for the last segment. So they are also using the truck for the route from the warehouse to distribution center, and then go back to the warehouse. But their trucks are equipped with drones and charging facilities. And all the passengers in the warehouse, the trucks, very similar to this scenario. The trucks will go through the route, and then you have the distribution point. Use the drones to replace the trailers, and for the last segment to the end users. And when all the drones finish the delivery, and then they will return to the truck, and then the truck will return to the warehouse. Okay, so this is the status. This is the current status. As mentioned before, for the current logistics, we are mainly using the trucks and the tricycles or trailers, and for very small proportion, they use the trucks plus the drones. So take a look at this diagram. This is a case study in Beijing. you have the route from the warehouse to the distribution point number 1, distribution point number 2. This is the truck route, right? Number 3, number 4, and then go back to the warehouse. So this is basically, this is the route of a truck route. And then you have the distribution point connecting with the trailers, and the trailers will finish the end users, to finish the last segment delivery to the end users. Then you may ask, why can't we use drones to replace the trucks? Because we don't like the trucks. The trucks are very slow. They affect our social vehicles, affect the traffic flow. The trailers are very irregular vehicles. They affect the traffic flow substantially. Why not using drones to replace the trucks and trailers? Okay, there are 2 reasons. Number 1, the regulations, but we can try to convince the authorities. But what are the technical challenges? What are the technical challenges? There are 2 reasons. Number 1, a drone's driving range is only around 20 meters or so, which is inadequate for city range delivery. The range is limited. Number 2, the cost per kilometer per kilogram is higher than the truck-trailer combination. To solve these 2 problems, my group will develop a new approach, a new device that allows the drones to land on the roof of vehicles. You see this diagram. This is the drone. The drone can land on the rooftop of the vehicles, the social vehicles, while the vehicles are moving, while the vehicles are in motion. With this tool, when we wish to move a box from one area to another area, for example, if we separate the Beijing city into a number of zones, you see zone 1 is the left up corner, the zone N is the right lower corner. So you want to move one parcel from zone 1 to zone N here. What we need to do is simply to find a social vehicle. You have numerous social vehicles in zone 1, and you want to find one social vehicle that intends to travel from zone 1 to zone N. Then we rent the rooftop spaces of this vehicle, and the roof spaces are currently unvisited, so we can pay a very small money to rent the rooftop space of that zone, of that vehicle. So to finalize the long distance delivery in between, and we send a drone for the first small segment from the origin to the rooftop of the vehicle, and then the drone will will take off for other tasks, and the parcel will stay in the on the rooftop of the social vehicle, and the social vehicle will take their predetermined route, the original route from zone 1 to zone N. As soon as the vehicle arrives at zone N, you send another drone to take the parcel off, and then fly to the final destination, right? Fly for the final destination. That means for the first very small segment, we use drones. For the last very small segment, we use drones. For the very long distance in between, we use the currently visited vehicle roofs. So you can imagine the problem is, it's very cheap, right? Because the long distance in between, you use the currently visited vehicle roofs, vehicle roofs. That means you can pay a very small price, very cheap price to have this service. Now we solved the above mentioned two problems. Number one, we don't need to travel for long time because you only need to travel for the first very small segment and the last very small segment, not for 20 minutes, even not for 2 or 3 minutes, only for two very small segments. Number two, the cost is very cheap because the rental for the currently wasted car route will be very cheap. It is very similar to the carpooling system by the Uber or by the Didi in China, the equivalent of Uber in China, Didi. So very similar, but the vehicle itself, they don't need to change the route, right? Because for the carpooling, you need to change the route, pick up the other passenger. So the route, you need to change the route, which is no good. So, but for this scenario, in this case, logistics version of Uber carpooling system, so you don't need to change the route because the drones are flying faster than the vehicles. Number two, you don't need to share your cabin spaces with another stranger, and because the parcel on the rooftop, you don't even see it, right? You don't even see it. Okay, for each catchment, because we can separate the city into a number of catchments, and for each catchment, we can allocate a few drones for the first segment first service or for the last segment service. For the other catchment is the same, and the parcel is carried by the vehicle from catchment one to another catchment where the end user is located, and another drone in the end user catchment flies to the vehicle, pick up the parcel, and deliver it to the end user. So with this system, if remember, this is the number one. The number one system is the current system in Beijing. The number two system is the system in research papers in the United States. And number three is all system. You can imagine, all systems will have the cost benefit because we are using the currently wasted rooftop spaces of social vehicles. So our cost is lower. And we will have the time advantage because you are flying and you solve the last mile, first mile problem. We have a time advantage. As such, more and more users will use this system instead of truck-trailer combination. In my group, we also have done the work using discrete choice model to estimate the market share for the current truck trailer combination and all system, and then we can replace a lot of trailers, which will improve the traffic condition, right? Because we didn't introduce any new vehicles, right? We didn't introduce any new vehicles, and we replace many trucks. No more trucks. The number of trucks are much smaller than before. Number of trailers are not much smaller than before. And we are not introducing new vehicles because we are using the rooftop of the currently wasted social vehicle space. So the traffic volume will be lower because you have less number of trucks, you have less number of trailers. We reduce the number of trucks and trailers, and we don't introduce new ground vehicles. And in this way, the less traffic on ground, so now the traffic volume will be reduced. Then the higher speed the vehicles will have, right? Because less traffic, then less crowded, you have higher travel speed. Then each and every passenger in the city will have their shorter travel time, will save their travel time day by day. That is a huge benefit for the society. That is a huge benefit for the society. We also estimate the social benefit for the city annually. Okay, the above example. Okay, I will speed up. because we may not have enough time for question and answers. So the above example is for logistics, technological speaking. There is no challenge, no much challenge, but for passenger transport in the vertical, 3-dimensional system, it is still, we are still waiting. But this example is about the passenger transport, and we also have done studies for the passenger transportation with flying vehicles. Actually, it's not a flying vehicles; it's eVTOL. It's a electric vertical taking off and landing devices. Because they are not able to drive, they can only fly. They are not land air amphibious. Here we only consider eVTOL. They can only fly. They cannot travel on road. We design a land-air cooperation system with the first, it's similar to the previous example, with the first segment and the last segment using land transportation, while the long distance in between using the eVTOL, the low altitude air transportation. So you see, for this catchment, all the passengers, you see for this catchment, all the passengers will travel through land transport from their home to the vertiport. That means the vertiport, the taking off space to the vertiport. And then you use the air transportation, the low altitude air transportation from one vertiport to another vertiport. And then you have the last segment. You have the last segment by land transport. Okay? To achieve this, we have to design the vertiport, right? To determine where we allocate the vertiport, how to arrange the traffic. This is actually a very huge study that we compares 12 largest cities in China and 10 largest metropolitan areas in the United States. We also use the high resolution travel time data. I'm not going to introduce the technical details. Again, I'm introducing a few findings. Okay, I need to fetch some water. Wait me for 20 seconds. Okay, I'm back. So the first, this is a vertiport diagram. You have quite a few vertiports in different cities, in Chinese cities, in the United States. So Chinese cities are more crowded, right? In Chinese cities are more crowded than the cities in United States. We thought at the very beginning, this system will work better for Chinese cities. And we move some trips up in the air, right? And then the traffic volume on the ground will be reduced, and then we will have shorter travel time, more substantial reduction in China than the United States. However, according to our study, the cities in the United States perform better in terms of travel time savings. So roughly around 40 to 50%, depending on different metropolitan area. But in China, it's only 30 to 40% reduction in different cities. This is because this vertiport, you see this vertiport, they also induce some local travel demand, which makes our local road more crowded. There is no much difference between the 2 minutes flying time and the 3 minutes flying time, because even the distance is very, very long, but travel time is short. So the total travel time will be dominated by the first small segment by land transport, and the last small segment by land transport. So the long distance in between is short, no matter it is 3, 4, 5 minutes flying time. So the total travel time, for example, 35 minutes, will be dominated by the first segment and the last segment. Because you have this vertiport, so for the local traffic, it's more crowded, and then the travel time for the first segment and the last segment in both China and the United States are longer than before. But the total travel time has been reduced for 30 to 40% in China, 40 to 50% in the United States. So as such, what should we do? We need to have the ground infrastructure adaptation to the new system. So we need to change the infrastructure nearby the vertiport area. Otherwise, the efficiency will not be high. Okay, another finding which is also very surprising, because people always consider battery. The battery is the biggest challenge for the eVTOL, for the flying vehicles. The battery is the biggest challenge. However, according to our study, even if the battery is more than adequate, we don't set any constraints in the battery. We will only travel for 3 to 6 minutes in China and the United States. We don't need to travel long time because the speed is high, it's within a city, the distance is not that long. So you don't need to travel too long time, 3 to 6 minutes. That means if you have 10 minutes to 15 minutes battery size, it will be more than adequate. So we don't need to have a large battery. We don't need very long time. The city size is relatively small. That is, if we can develop batteries of 10 minutes range, 12 minutes range, that will be more than adequate. Even if we have 30 minutes flying time for the urban area, we will use small battery. We don't need to use bigger battery, because bigger battery, that means heavy. It's heavier, no good for the flying vehicles. This diagram is the problem that I mentioned just now. You see the green links, roads. That means those green links, the traffic volume will be reduced, and the red links, that means the traffic volume will be increased. So take a look at the demand representation, and it can be seen clearly in the diagram. The long distance travel demand is smaller. You see all the long distance, it's green, right? It's smaller. But the local traffic, for the local road, the volume has been increased. The local road nearby the vertiport is much busier than before. So we need our road infrastructure, as I mentioned just now, we need our road infrastructure adapted to the change before implementing the new system. Okay, to end today's 3 case studies, it's a very lengthy presentation. So I need more water. I share with you a few thoughts, a few of my thoughts. We are in the era of revolution in transportation area. We are in an area of fast changing, fast developing nowadays, and we need more talent working in this area. And we have 3 points. Even for the general engineering, the 3 points are very important. Number 1, engineering is increasingly interdisciplinary. We need interdisciplinary collaboration between, transportation engineering, vehicle engineering, electrical engineering, computer science, social scientists, even lawmakers, because we are talking about the regulations of a low altitude vertical transportation system. So interdisciplinary is very important. Number two, this is a very practical discipline, relying heavily on the government investment, and also the government gets the total. We have the huge social benefit. That means the government gets the biggest benefit. For example, if we use the drones to replace trucks and trailers, is the biggest beneficiary is not the logistic company. The biggest beneficiary is the government, because all the citizens, all the residents will enjoy shorter travel time, shorter commuting time. Then the valuable time multiply their time savings. That's a huge number of benefits, social benefits. Okay, number three is we need to look at the future development need. We need to look at the future development need. We need to focus on the area of high growth. We shouldn't focus on what the operation is now. We should focus on what will the operation, what's the future operation will be in future. As I introduced earlier, I taught in a few very different countries, and as a professor, I attended quite some outreaching activities with young students, with high school students, senior high, junior high, with junior bachelor students, undergraduate students. So I found 3 points are very important. Number one, happiness is actually generated from doing what you love to do, not by the return when you earn a lot of money, right? Happiness, the genuine happiness, is actually generated from doing what you love to do. We need to find our genuine interest and follow your genuine interest. And also the perfection, in Chinese we call it 止于至善, aiming at the absolute perfection. So this is another very important deciding factor for your success. I often use this diagram. You see this diagram. I have often used this diagram in my lecture to my PhD students. This black curve is our current boundary of knowledge. Within the boundary, we know the knowledge. Outside of the boundary is unknown knowledge. So if you are at the boundary, if you are at the knowledge boundary, on some opportunities, on some occasions, we may find a way to make breakthroughs. However, if we are not aiming at the best, we are close to the boundary. If you are here, not close to the boundary, but not at the boundary, not on the boundary. Even if you have opportunity, you have that opportunity, there is no way for you to make a breakthrough. So as we are not at the boundary yet, so your perfect product is your core competitiveness. Number three is diversity. This is the reason why I love to attend the event like this, because we need to meet more people. We need to meet more people. We need to talk more people. Especially we need to meet people from different countries, different background, different culture, because we want to have diversity. Because diversity generates creativity. At a homogeneous environment, your mindset is very likely to be confined, to be fixed, without thinking out of the box abilities. Okay, this is the 3 advice that I want to give to you. So that's all for my presentation. I'm happy to take any questions if you have. So if you can unmute yourself, you ask your question, or you can raise your hand with the raise hand function of Zoom, and then the moderator will call your name, you ask questions. Alternatively, you can also type in your question in the chat box. Okay, if you have any questions, let me know.